So the first question asks us to find the angle here, and we're given alpha, beta, and the incident angle, which are here, here, and what I first did was find out if there were any angles that we can find for. So here we have a line, and we know 70 and we know 36, so I just did 180 minus 70 minus 36 to find the angle 74 degrees. And after finding this angle, I noticed that here it was a right angle because this is the normal line and this is the surface, and the normal line is always perpendicular to the surface, so here is always perpendicular. And since we already know the incident angle here, we can just do 90 minus 53 to find 37. And when they're and then the incident angle is always equal to the opposite incident angle, so the one opposite the normal line, and so that's why 53 is equal to 53 here. We know that since these two are both right angles, this is just going to be 37 degrees, and 180 minus 74 minus 37 is going to be 69. And then I use a similar principle, 90 minus 69 equals 21. That's how I got 21. This question asks us to find the speed of light in the new medium. So recall this equation where the refractive index is equal to the speed of light, which is a constant, over the velocity in the new medium. So rearranging this top equation, we get this, and then we just need to plug in the values. C is always going to be equal to this, so you can just have that memorized. 3 times 10 to the power of 8. And n we're given here, so I just plugged it in here. N is unitless, so I didn't put any units here. And that's how I got this value. Yeah, and here's just a little diagram on what's actually happening. And then I have this question, which asks us to find the wavelength. So first I found the velocity. I have the speed of light over the refractive index equals the velocity. And so speed of light is the same, and refractive index we're given here, and I found the velocity using that. Second step is to find the frequency, and this is probably, I think it's in the formula sheet. So you just do V equals lambda times frequency. And to get an intuition on why this is true, lambda is in meters and frequency is in seconds inverse. So it would be something like meters per second. Yeah, it has the units of meters per second, which is the same thing as the velocity, the units for velocity. So we need to find the frequency because the frequency always stays the same, regardless of where you're in. So regardless of whether you're in air or in water or whatever, frequency is always going to be the same. It's the wavelength that always changes. So since frequency is always going to be the same, we can find frequency when the light is in a vacuum. So I would just use this equation because c is the speed of light, and that's why I would do c equals lambda times the frequency, and then this lambda corresponds to the light's wavelength. So this 659 is the light's wavelength in a vacuum, and that's what I would put in here. And so I put in the speed of light and the wavelength in a vacuum, and that's how I got this frequency. This equation is you can only use this in a vacuum. And since the frequency is same for wherever you are, you can use that same frequency to now find the wavelength for your light. Yeah, and then we found the velocity from before, so we can just plug the values in and see we're using the same equation as this one. I just plug in the values, I get the velocity, which is from here, and I put in the frequency, which is what we derived from here, and that's how I got this value. And the answer is asking to find it in nanometers, so I just go back one step to negative 10 to the power of negative 8, and then go back one more step to 10 to the power of negative 9. And that's how I got 433.55 nanometers. This question is asking us to find this angle, and so we just use Snell's law, which is n1 sine 1 equals n2 sine 2. We just plug in the values. Basically, since we're going in from this direction, n1 is going to be 1.23, and we just put in the theta value here, and then we set that equal to n2, which is just 1 because it's in air, and we find theta 2. So here's my working if you want to follow along. For this question, they're asking us to find the ray's angle of refraction. It's the same thing as this one, basically. And then I just solve for theta. Yeah. So one thing to note is that when you do these questions, just make sure to write down n1 and n2 and whatever other values you're given. That way you can organize your thoughts better, and you might get more points actually in the test. Okay, and this question asks us to find the refractive index now, and we use Snell's law again. There's a lot of questions with the Snell's law, so sometimes I just like to write the equation without even seeing after I read the question, I like to just write it down first and see if I can use the equation. Here we're given n1, and we're given theta 1. We're also given theta 2, so we just find n2. And here's my working. You can always pause the video to see my working better. This is the first question with the critical angle. So that's basically when the light doesn't leave the surface. So the ray comes in, and then it's supposed to go out like this, but it comes in at such an angle so that it doesn't go out. And eventually, if you increase it even more, it's going to start coming in. And you see this when you shine a laser beam towards water, and then you can see how sometimes in the water the laser beam it just comes out like that. I don't know if you know what I mean, but anyways, for this question we need to always use theta 2 as 90 degrees, because essentially theta 2 is the angle from the normal to the refracted ray. Normally it would be like this, so this would be theta, or it could be like this, and this could be theta. But now, since it's not going out, theta becomes this angle, which is 90 degrees. So when we have a critical angle question, the refracted ray is always going to be inside. It's not going to leave. And when we have that, we always use theta 2 as 90 degrees. And here we see that sine of theta 2, 90 degrees. This is just going to be equal to 1. So it really simplifies the process. And here I just plugged in n2 equals 1. So actually, since n2 is equal to 1 and sine theta 2 is also equal to 1, this whole top value just becomes 1. Yeah. Here's another question with critical angle. So yeah, this time they're asking us to find the index of refraction of the fluid, and it's basically just the same process. This whole thing is going to be equal to 1 since n2 is equal to 1, and this angle is 90 degrees, and then we just solve for n1. Yeah, they also give us the angle, so yeah, it's just plugging in. Question 9. Okay, so this time we're going in from, there's no air, so they both have index of refraction, and we're going in from here to here. This time we're trying to find this theta value. We know that, okay, it's flipped upside down, but it's still the same concept, because the refracted is this theta, so this is supposed to be theta 2, and since we want the critical angle, we want this theta 2, and then this is 90 degrees. So we set up Snell's law again, and we see that since the sine of theta 2 is equal to 1, we can just cross that out and set it equal to 1. And this value, however, is not 1, so we need to plug in n2 here. And then we just solve for theta 1. Yeah, because we're given n1. And theta 1 corresponds to this angle here. Okay, this question was probably a little bit tricky. There's actually a quick method to solve this question. we have to work backwards because we're given these values and we're not given a lot of information here. Yeah, so let's start from this section. We're going to find the equation for the middle ray first. So the green part corresponds to this ray, and the orange part, the yellow part, corresponds to this section. So I set up the Snell's law equation. Here we're given N2 is equal to the air, so it's just 1, and theta 2 is also 90 degrees since it's critical. It's a critical angle question, so this whole thing just becomes 1. And then I plugged in the values for the glass and this critical angle theta. And I just set this value equal to 1, and I didn't solve for anything because you'll see why. Because we're going to use this again, and when we use it again, we can just substitute this instead of having to solve for it everything again. So step 2 is to find the incident angle. So now we're going to be dealing with this part. And we see that the incident angle is this, and N1 is the fluid. This section is then going to be equal to this section, and we see that this is the exact same expression that was here. So we can just substitute this whole thing for 1, since this 1 was from this section. Yeah. So if we use this little trick, you can do it much more faster. We can do it much more faster. And so we're given all the other values. N1 is the fluid, and we solve for the theta incident angle. And yeah, this is the theta incident angle. And this is this value. Next question. This is a similar question. So first we're going to solve for this section. And for these types of questions where it's like the critical angle question, except like the ray is like going from here to here to here, like it's better to solve it. It's better to solve this part first. So it's better to solve it backwards, basically. So we set up Snell's law, Snell's equation, and this whole section is just equal to 1 because it's an air, and this is the 90-degree angle. So it really simplifies the process because we already know N1 is this value, N of the glass, and we find the angle here. This angle corresponds to this angle, by the way. Yeah. And then we can actually use the triangle here. See, because there's a triangle here, and there's a 90 degree here. And we know this angle, and this is also 90 degrees, so we can solve for this angle. And then using this angle, we can also solve for this angle. Yeah, and here it's also 90 degrees. And so since this angle was 50.8 degrees, we can just do 90 minus 50.8, so 90 minus 50.8 from here to get 39.2. And that's how we get theta 2. And so then we're going to solve for the blue section, which is this section. We set up Snell's law, Snell's equation, and we solve for theta 1 because we are given N air, and we're also given N glass, and this value. So yeah, that's how you just solve for, you just plug in the values and you solve for it. Okay, this question comes up sometimes, so yeah, make sure to do this one properly. Basically, it's like you kind of have to like imagine that, like rotate the page and like imagine that this was just like here. Then it's just gonna be like the ray just comes in and it's like your regular question. Yeah. So for these types of questions, it's really important to see where the normal line is first. And here we see that the normal line, it's always going to be perpendicular to the surface. So for these types of questions, draw the normal line first, and then we can put in all the angle values. So after you draw the normal line, we see that this triangle is similar to this triangle because these two lines are parallel. 45 degrees, 45 degrees. They're going to be equal. And since this is perpendicular, we see that this is also 45 degrees. And then since these two lines are intersecting, here's 45, so it's going to be 45 here as well. Yeah. And so theta 1 is going to be equal to 45 degrees, and theta 2 is going to be equal to 45 plus this extra theta, because it's about the normal line. So it's this angle. Yeah. And I just plugged in all the values here, used Snell's law, and that's how I solve for n1, which is here. Yeah. Okay, yeah. Also, when you solve this question, some people might have gotten an index of refraction that's less than, like, I don't know, something like 0.8 as the index of refraction. And remember that the index of refraction can never be below 1. And this is because the index of refraction equation comes from this, and it's basically the ratio between the speed of light when it's in a vacuum versus the speed of light in the new substance, like water. Yeah. So this is going to be the maximum possible speed. So this value is always going to be greater than this value, because you can never get a light that travels faster than in vacuum. So this value is always going to be greater than 1.